So next speaker, Dr. Bryant McNeil from the OC University, and we'll be talking about disorder-induced ferrimagnetism in these manganese cobalt germanium films.
All right, thank you. Hello, everybody. I'm going to talk today about manganese cobalt germanide films with varying manganese concentration and how atomic disorder will actually cause this unexpected ferrimagnetic ordering. So the original motivation for this work was actually to grow the tetragonal Heuser alloy manganese 2 cobalt germanide, but instead we found that all of our samples formed this metastable hexagonal polytype of manganese cobalt germanide. This is still interesting though because our film exhibited an unexpected ferrimagnetic structure as compared to the ferromagnetic manganese cobalt germanide hexagonal structure. And so in our paper, we attempt to model this ferrimagnetism using a density functional theory. We calculate the magnetic moments as a function of disorder, and we also calculate a sublattice-based mean field model to help give some merit to our claim that these are ferrimagnetic films. So manganese cobalt germanide has two phases, a low temperature orthorhombic phase and a high temperature hexagonal phase. So we observed both of these, but I'll be talking today about the hexagonal type. So in the ordered structure, it's got 5.56 Bohr magnetrons per unit cell. Most of the moment is coming from the manganese atoms with 2.4 Bohr magnetrons each, but there is a small moment on the cobalt 2C sites. So we grew compositions, varying compositions of manganese. So we started with X at 0.8, so manganese deficient samples. And in between those, we also have compositions ranging up to X equals 2.5. So we have manganese-rich samples as well. So we use X-ray diffraction to characterize the structure. Here you can see a representative X-ray diffraction pattern. So the films were grown on oxidized silicon wafers, and they were annealed ex situ. So all of our films that we observed formed this nickel-2 indium type structure, and here's the representative X-ray. We also have an atomic force micrograph here, which you can use to calculate the average grain sizes. So when you corroborate that with grain sizes calculated with X-ray diffraction, we find that they're in agreement, which does not give any evidence for any secondary phases. So the main result of this X-ray diffraction fitting is that we've got this nickel-2 indium structure, as well as the fact that there's either a preferred orientation towards some peaks, which is induced by the annealing, or that could equally be explained by vacancies on the cobalt 2C site of up to about 25%. But unfortunately, using X-ray, we actually can't tell the difference between the two. So moving on to the magnetometry, we find that all samples have qualitatively similar hysteresis loops, except that the manganese-rich samples have a larger coercive field and the curves are much rounder, which indicates a larger anisotropy. In terms of the moments per unit cell here, we find that they are much lower than that of the ordered structure of 5.56 Bohr magnetrons per unit cell. And so that was quite interesting, and I'll be explaining that in a little bit. When we look at the remnant magnetization, we find something that is distinctly different from a ferromagnetic curve, that is expected in the ordered structure. We have a compensation point here where the magnetization actually reverses sign, and this is distinctly a ferrimagnetic property. Although we do have an uncompensated curve for the manganese-rich samples, we go on in our paper, and I'll talk about this in a bit, to argue that all of our samples that we observed actually exhibited ferrimagnetism. And so for completeness, here's all of the curves. So for manganese-rich samples, we have the uncompensated ferrimagnetism, and for the manganese-poor samples, we have this compensated ferrimagnetism, where the magnetization actually reverses sign. So in order to explain this, we performed density functional theory calculations. Since we are off stoichiometry from manganese cobalt germanide, we do expect there to be some atomic disorder. And so what we do is in this panel, we are taking manganese atoms and we are replacing them on the cobalt site. And over here, we are taking manganese atoms and we are replacing germanium. And in both cases, we find that when manganese occupies either the 2C or 2D site, its moment couples anti-ferromagnetically with the moment of the manganese on the 2A site. And there's also a compositional effect as well. So in order to model the reduced moments, we calculated a model in our paper which allows us to determine the moment per unit cell as a function of the manganese concentration, as well as an additional disorder, which we are calling delta. And there are two main mechanisms that we use for this. So in the manganese-rich samples, we have excess manganese atoms, which are being pushed onto the 2D and the 2C sites. And in manganese-deficient samples, we have disorder that is moving manganese to the 2D site. So by comparing our calculated moments with those that we observed, we can get an estimate of the additional disorder. So for the manganese-rich samples here, this line corresponds to about 3% disorder, and this line here corresponds to about 17% disorder. We also performed a mean field model to help quantify the effect of these manganese disorder, as well as to show that this is indeed ferrimagnetism for all samples. So what we do is we transform this manganese cobalt germanium unit cell into a 2 sublattice model. So we use the Nayel model here. And so our 2 sublattices are as follows. We have the A sublattice, which consists of atoms on the 2A site. And then we combine all of the atoms on the 2C and 2D sites into a B sublattice. So the A sublattice will have moments that point upwards, and the B sublattice will have moments that are opposite to that. So the molecular field acting on each sublattice is given in terms of the sublattice magnetization and these coupling constants here, which are related to the Heisenberg exchange energies. And by solving these nonlinear equations, we can determine the magnetization as a function of temperature. So the shape of the magnetization versus temperature curve is determined by these parameters. And the moments as well will determine the temperature or the magnetization at low temperature. So we're able to fit the remnant magnetization for this manganese deficient sample here. We're able to capture the dip in the magnetization. We're able to capture the compensation point. And we're also able to obtain a fit for the x equals 2.5 as well. And you'll notice that they are different. So I mentioned earlier that there is a difference in anisotropy between the manganese-rich and poor samples. So we attribute this magnetization up here due to domain relaxation. So what we do is we actually fit the, we get rid of the low temperature remnant magnetization, and we actually scale the moment up. And so here is here's what is performed for all of our samples. So we are able to obtain a fit. In terms of results, we find that the inter-sublattice exchange constants, so here between the A and the B sublattice, they're anti-ferromagnetic, and they increase in strength with manganese composition. And the intra-sublattice interactions are ferromagnetic for the manganese-poor samples, and they actually change sign for the manganese-rich samples. And so we use our previous model to estimate the magnetic moments for this modeling. And then when we perform a refinement of these fits, we find that the calculated moments here, they agree with these open squares here for the DFT moments. So to conclude, we've shown that anti-site disorder will drive the system from ferromagnetism into ferrimagnetism. And we can explain the reduced unit cell moment by the fact that the disordered manganese will couple anti-ferromagnetically to the manganese on its original site. So this here is a phase diagram of the coupling parameters, which gives you different types of ferrimagnetism. So in the manganese-rich samples, we find that we have this Q-type ferrimagnetism that is uncompensated. This here is the location of one particular sample on that phase diagram. And in the manganese-poor samples, we have the disordered manganese giving a compensated V-type ferrimagnetism. So I'd like to thank everybody on the screen and NSERC for our funding, and I'd like to thank you for listening, and I'd be happy to take any questions.